Okay, I am going to try to finish up Chapter 17 today on electric potential, and the topic we'll be dealing with mostly is how to use this concept of change in potential, potential difference, to tell us about the behavior of electric fields inside matter, particularly inside insulators. We already have some idea of what happens inside a conductor, and we'll start there first as an example. And we had a question at the very end of class last time, so I want to start with this example of a capacitor. So we have two metal plates. One is positively charged, and one is negatively charged. Okay, so capacitor inside the gap in between the two plates, and let's say this distance is S, and what is S equal to? Let's say S is 2 millimeters, so 2 times 10 to the minus 3 meters. It's a charge plus Q and a charge minus Q, and let's say point A, location A is right on the edge of the positive plate, and location B is exactly opposite to it on the negative plate. And what do we know about the field inside a capacitor? Inside this capacitor gap, the electric field is pointing what direction? To the right, okay. And the magnitude of it is what? Q over A over epsilon 0. You had to use this last night for a homework set. So the issue is that it's in the approximation that this distance S is much smaller than the size of the plate. So the radius of the plate is stretching far beyond what we can see right on the board. It's a small gap, and so the field is mostly uniform inside. We can use this constant field approximation. So in fact, I'm not even going to worry too much about the charge or calculating the field from the area. Instead, let's just say that we know the potential difference, VB minus VA. And let's say that's negative 1,000 volts. And let's double check that the sign is correct, because if we're going, VB minus VA is telling us we're going along a path that goes from A to B, and we're going in the direction of the electric field, so the potential difference should be negative. Okay. So, what's the electric field? Well, VB minus VA is negative E dot delta L. And I already know the direction, so let me just find the magnitude. The magnitude is going to be the magnitude of VB minus VA over the magnitude of that distance, and it's really delta x here, right? Because we're just looking at EX delta x. It's only in the x component. So that delta x is the same as the distance S. Okay, that's the separation. So we have 1,000 volts divided by 2 times 10 to the minus 3 meters. And that gives you an electric field of 5 times 10 to the 5th volts per meter. Okay. Now, I've got the same capacitor, same charge on the plates, same distance between the plates, same everything, except I'm going to do one thing. I'm going to insert in between the plates a slab of metal. So I'm just going to put a great big parallel sheet of metal that has some thickness. This is metal here. Okay, and so this plate is still positive. This plate is still negative. And let's say the distance, let's say this is 0.5 millimeters from A to this surface of the metal. This is a 1 millimeter thick metal slab, and this is another 0.5 millimeter. Okay. What happens? What happens to the metal? Okay, let's be careful. It's neutral. It's a neutral slab of metal. So is it going to end up with a net charge? No, but what is going to happen? It's going to polarize. It's going to polarize. So what's going to happen on this surface? Becomes a negatively charged. Okay. So and this side positive. Okay. So I just want to be careful about the language. It's polarized, then it's still neutral. The net charge on the entire metal slab is 0, but it has a separation of charge now, negative on one side, positive on the other. Okay. So here's an idea that we should all be familiar with by now because it showed up on homeworks and quizzes and again on the tests, right? What is the net electric field inside the metal? 0. Okay, so E net's equal to 0. But that net electric field is due to two contributions, right? We still have the electric field of our original capacitor, which is pointing in what direction? To the right. So I'll say this is E of the capacitor. So that means what? E of the induced charges or the polarization charges on the surface of the metal has got to point to the left. And what do we know about that E on the metal? That electric field is got to be the same as the E on the capacitor. So the electric field of the metal is going to be what we just worked out. The magnitude of it is going to be 5 times 10 to the 5th volts per meter. Okay? Now, our job is to figure out two things. One is, well, it's kind of one related thing, but how much charge is on each side of the metal, and then what is the new electric field inside the capacitor, or inside the gap, inside these air gaps within the capacitor, a point here and a point here. And let's think about the metal first. Squint your eyes and kind of hold your nose and ignore the presence of the plates for just a second. And just think about this polarized slab of metal. Here's one surface that's positively charged. Here's one surface that has the exact opposite negative charge, parallel to each other. Inside, what does that look like to you? It looks like another capacitor, doesn't it? It looks kind of like another capacitor. So the electric field due to the metal, the charges on the metal, should in fact be equal to Q over A over epsilon naught. Well, it's the same area as our original capacitor. There's no dependence on the distance, right? Because if the gap is small enough, then the field is uniform. So how much charge ends up on this side? Let's put it this way. Let's say this is some positive Q, all right, and this is negative Q. How much charge ends up on this surface? Negative Q, right? Because if this field is the same, then this charge in this formula has got to be the same. And so you end up polarizing. Negative Q on this side, positive Q on that side. Now, squint your eyes and hold your nose again and look at just sort of this half of what we've got. We've got positive Q here, negative Q here on this surface. In between, what have we got? Another capacitor, right? Now it's sort of like having two capacitors, one after another. So what do you think the electric field in here is going to be? Should be the same as it was before. Should be the same as it was before. Approximately, okay? Because we're ignoring one thing. We're ignoring the fringe field, okay? This polarized slab, okay, behaves like a capacitor itself, but there is a small amount of field that it makes outside of its borders. Okay, we talked about that being the fringe field, the field outside of a capacitor. But if we ignore that small amount, it's going to be small compared to the field inside. The electric field in here should be 5 times 10 to the 5th volts per meter. The electric field in this air gap should be 5 times 10 to the 5th volts per meter. And in here, the net electric field, we said, is equal to 0. Okay? So now we have sort of 3 regions, one after the other, with 3 different uniform electric fields. Okay, there's a lot of stuff here, so let me kind of clean this up. And let's see, we'll get rid of this. And we still have our 2 locations, A, which is over here, and B, which is over here. Okay? So here's the question. Here's the question. Without the metal slab, when we found potential difference A to B, it was negative 1,000 volts. Then we put this metal slab in between. What's VB minus VA now? Okay, we have 2 popular answers. Some people are saying answer number 5, which is exactly the same as it was before. Some people are saying, well, it's half of what it was before. Well, how did we deal with a situation like this last time? You have a path that goes from A all the way over to B, right? As you traverse the imaginary path, you cross through 3 different regions of uniform field, differing uniform field, right? From A to this surface, it's 500 volts per meter, but then across this 1 millimeter distance, it's 0, and then it's back to 5 times 10 to the 5th volts per meter again, okay? So how do I deal with a situation like that? How do I find the total delta V? What do? We add them up, right? We take one at a time, find the delta V across the first region, then across the second region, then across the third region, add them up. So we have an E1 dot delta L1, right? Minus an E2 dot delta L2 minus an E3. Don't need this anymore, so erase this. E3 dot delta L3. And so we have E1, the X component of E1 is 5 times 10 to the 5th volts per meter. And the distance across that first region is half a millimeter, right? 0.5 times 10 to the minus 3 meters. Minus, what's E2? E2 is 0. E2 is 0. And then minus 5 times 10 to the 5th volts per meter times another half millimeter distance. So that's the same, so we can add them up. Just say it's going to be twice that. What do you get? Should be negative 500. Okay, so it does actually reduce the potential difference. The field, placing the metal slab inside the capacitor doesn't change the field in the air gap, doesn't change this field in the air gap, but does reduce the field inside to 0, okay, because it's a metal at static equilibrium. So it's sort of polarized perfectly so that we cancel out the net electric field inside, and then when you take the potential difference, you're going through a rather large region where the electric field is 0, giving you a delta V equal to 0. You've reduced the potential difference overall. Okay? Questions? All right.